Circular motion. For today, we are looking at circular motion. If I tie a rope to a stone and I wire the rope along a circular path, such as this will be the length of the rope that I tied to the stone. This is the stone. At this point, the stone will have a velocity in this direction. This will be the velocity of the stone at this point. This is because the velocity is always tangential to the circular path. The velocity of the object is always tangential to the circular path. By the time the stone gets here, this will be the direction of the velocity of the stone. This will be the direction of the velocity of the stone. Alright, now what we can pick from that is that we need to first write an equation for the acceleration of the stone. We need to write an equation for the acceleration of the stone. Okay, now the acceleration of the stone is given by A is equals to V square divided by R. Our acceleration is equals to V square, that is the velocity square, divided by R. The first thing we need to know for an object that is performing circular motion is that the velocity is changing, the direction of the velocity is changing, such as the velocity that it has at point A here and the velocity that the stone has at point B. Since the velocity is changing, the object will have acceleration. Since the velocity is changing, the object will have acceleration. So the stone in this case will have acceleration. Okay, now if we are to calculate that acceleration, and of course that acceleration is called centripetal acceleration. Centripetal acceleration. And if we are to calculate that acceleration, it is equal to, the magnitude of the acceleration is equal to V square divided by R. That is the velocity, the square of the velocity or speed divided by the radius of the circular path. Okay, this is the radius of the circular path. The radius of the circular path. Now, since the object has acceleration, the object will also have a force. There will be a force, okay, on the stone. The stone will experience a force. And we already know that to get the force on an object, we will multiply the mass of the object and the acceleration of the object. To calculate the force on an object, we'll multiply the mass of the object and the acceleration of the object. Now, in this case, the mass of the stone is still m, but we have written a formula for the acceleration of the stone, which is v squared divided by r, which is v squared divided by r. So in this case, our force, the force that will be experienced by this stone that is whirled in a circular pattern, will be mv square divided by r. mv square divided by r. Okay, and of course this force is called centripetal force. Centripetal force. Okay, so this force is called centripetal force. And don't forget, the direction of the acceleration will also be the direction of the force. The direction of the acceleration, okay, which is the centripetal acceleration, will also be the direction of the force. And take note, the direction of the centripetal acceleration, looking at our diagram, is towards the center of the circular path. The direction of the centripetal acceleration is towards the center of the circular path. Okay, therefore, the direction of the centripetal force will also be towards the center of the circular path. The direction of the centripetal force will also be towards the center of the circular path. And this is the reason why the tire of a car that steps into mud, okay, the mud will fly away from the tire as the car is moving and the tire is rotating. The mud will fly away in a direction that is tangential to the circular path. In a direction that is tangential to the circular path. Okay, there's one more force that we need to take cognizance of, and that force is what is called centrifugal force. Centrifugal force. Okay, so centrifugal force acts in the opposite direction to the centripetal force. So centrifugal force is equal to the centripetal force and acts in the opposite direction. Okay, so centrifugal force. Okay, so centrifugal force is equal to the centripetal force and acts in the opposite direction to the centripetal force. Okay, so apart from that, let's now write an equation for the angular velocity. Let's write an equation for the angular velocity. Okay, so for the angular velocity, I have angular velocity we'll represent that with this symbol omega. We'll represent angular velocity with this symbol omega, and that is equal to the same way velocity is displacement over time. In this case, look at this. The stone is here. The direction of the velocity is in this direction. When the stone gets to point B, the direction of the velocity is in that direction. Okay, so let's draw the length of the rope, which is also the radius of the circular part. Okay, so for the stone to move from point A to point B, it must have covered some angle. Okay, it must have covered some angle called theta. For the stone to move from point A to point B, it must have covered some angle called theta. Okay, so if we are to define angular velocity, okay, so angular velocity is in terms of the angle. So we'll say is the angle turned divided by the time taken. Angle turned divided by the time taken. If we check that properly, our angle turned, as in this diagram, will be theta divided by the time taken. Theta divided by the time taken. Okay, so we can write that angular velocity is equals to theta angle turned divided by t, which is the time taken. We should take note of that. What about our normal linear velocity? For our normal linear velocity, the definition is velocity. Okay, velocity v is equals to displacement divided by time taken. Displacement divided by time taken. Okay, so let's write that our displacement. Now look at something. Go back to this diagram. If we go back to this diagram, for the stone to move from point A to point B, it must have covered some distance s. The stone must have covered some distance s in moving from point A to point B. Okay, moving from point A to point B, the stone must have covered some distance s, and the distance covered is along the circumference of the circular part, and the distance covered is along the circumference of the circular part. In that case, I can write that my v is equals to, that is my linear velocity. Okay, my linear velocity is equals to s divided by t. Okay, which we can write that v is equals to s divided by t. Okay, all right, we are good to go. Now let's see, is there a relationship between our angular velocity and our linear velocity? Is there a relationship between angular velocity and linear velocity? Let's check that out. If theta, okay, if angle theta is very small, okay, if angle theta is very small, it has been proven that theta will be equal to s divided by r. If the angle turned for this diagram is very small, so small, our S, which is the displacement along the circumference from point A to point B, okay, divided by the radius of the circular part, okay, will be equal to the angle turned. And from here, we can write that our S is equals to, if I cross multiply, S is equals to R theta. S is equals to R theta. Okay, so if this is my equation 1, this is my equation 2, and this is my equation 3. Okay, so if I put equation 3, okay, put equation 3 into equation 2. If I put equation 3 into equation 2, that will give me, I will have that V is equals to R theta divided by T. Okay, so I put equation 3 into equation 2. I will have that V is equals to, instead of S, I will put R theta for S, R theta divided by T, divided by the time. But take note that I already know what my theta divided by time is, and that will give me V is equals to R, okay? My theta divided by time is my angular velocity. That is my angular velocity, okay? That is my angular velocity, okay? So this gives the relationship between linear velocity and angular velocity. This gives the relationship between linear velocity and angular velocity. All right, take note of that. All right, having said that, we can go further to do some calculations. And that calculation we are going to do in the next class. Goodbye.